We've seen how scaling relations can help us understand the activity of catalysts and predict new materials. While correlations between the energies of transition states and reaction intermediates simplify the problem of describing the rate, they can also place fundamental limitations on how active catalysts can be. Let's see how this works. So let's consider the electrochemical reduction of CO2 to CO over metal surfaces. If powered by renewable electricity, this reaction could produce carbon monoxide that could be upgraded downstream to many useful products. So this reaction can proceed through the following elementary steps. CO2 undergoes a proton-coupled electron transfer step to form adsorbed COOH. That COOH molecule can be dehydrated through another proton-coupled electron transfer step to form adsorbed carbon monoxide and water. And finally, CO can desorb from the surface of the catalyst. So our overall reaction here is CO2 reacting with 2 protons and 2 electrons to form CO and water. The 2 protons and electrons are produced by a corresponding electrochemical oxidation reaction, such as water oxidation. So in this CO2 reduction reaction, we have a scaling relation between our 2 adsorbed species, adsorbed CO and adsorbed COOH. Now the scaling relation exists because both adsorbates bind to the surface through carbon. So their molecular geometry looks something like this. So surfaces that bind COOH very strongly are also going to bind CO very strongly. So here this scaling relation between the adsorption energies of COOH and CO are plotted, where metals over here on the right, which bind both intermediates weakly, are going to be limited by CO2 activation to form adsorbed COOH. Meanwhile, metals over here on the left are going to be limited by CO desorption from the surface of the catalyst. So essentially, our concentration of vacant sites is going to be very small on these catalysts. But if we look at a reaction coordinate diagram, we'll see that neither set of metals has ideal activity. So let's look at the reaction coordinate diagram without barriers, so just looking at the reaction energetics only. So here the overall reaction is close to thermoneutral, so the reactants and products have similar energies. So the ideal catalyst would have an energetic profile that looks something like this. So there's no step that's significantly uphill that limits the rate. If we look at the reaction coordinate diagram for something like gold, it would look something like this. So we can see that even though CO desorption is thermodynamically favorable, that first step of activating CO2 is very thermodynamically uphill. Conversely, if we look at a metal like platinum, the reaction coordinate diagram will look something like this. So here it's thermodynamically downhill to activate CO2 and form COOH, but then once we've formed adsorbed carbon monoxide, it's very thermodynamically uphill to desorb this from the catalyst. So essentially we're going to be stuck in this thermodynamic well. Now what the scaling relation tells us is that we can't independently move the reaction energetics for COOH and CO. So if I move this step down, this one will come with it. So if I start with a catalyst like gold, I could increase activity by decreasing the energy for that first step, but eventually if I do so, I'm going to get into a situation that looks like platinum where the second step becomes thermodynamically limiting. So this can be seen on this activity map. So what the scaling relation tells us is that we can move along this scaling relation line, but we can't move off it. So we can't independently say stabilize COOH, which would be moving down without changing the CO binding energy. And this is exactly what we would like to do to access the highest activity. So again, the reason why this scaling relation exists for metals is because they can't differentiate at a molecular level between COOH and CO. The stability of both adsorbates is dictated by the strength of the metal-carbon bond. To access higher activity, essentially what we need to do is break this scaling relation by designing an active site that can differentiate between COOH and CO and therefore decouple their binding energies. One way of doing this would be to use 2 cooperative sites, which I'll label A1 and A2. So since CO binds in this vertical geometry, its binding energy will be unaffected relative to a pure A1 active site, but if A2 has a strong affinity for oxygen, it could form a sort of interaction that looks like this. So in this way, we could move off the scaling line, stabilizing COOH without changing the binding energy of CO. It's no coincidence that the carbon monoxide dehydrogenase enzymes use nickel and iron metal centers that act cooperatively to stabilize COOH relative to CO. So calculations for the binding energy of these 2 intermediates on these active sites are shown here in green. And we can see that they fall off the scaling line and can access much, much higher activity. So here we've seen that scaling relations can impose limitations on the activity of metal catalysts by not allowing us to independently optimize the energetics of different reaction steps. We've also seen that three-dimensional active sites, such as those present in enzymes, can overcome these activity constraints.